let's get started. So I sent a number of announcements this morning. So hopefully all of you saw that. So the midterm result is out. I think all of you did a pretty good job. For the final will be next Wednesday. So the format will be exactly the same as the midterm. 5 problems, right? Is comprehensive, but you may expect at most 2 problems from the midterm before the midterm, and most of them will be after the midterm. Okay, so basically I'll give you another information inequality to prove. So probably that's the only part covered in the first half. Okay, yeah, because that is normally very important, and some of you made some mistake in the midterm for question 1. Okay, and what else? Oh yeah, and we have another homework. So homework 4 will be due on this Friday, I think. So we'll have another homework. It's very short. I think it's like 6 or 7 problems. So from chapter 10, and so the final exam will be 1 problem from chapter 10 and 1 or 2 problems. So that'll be very similar to your homework. All right. So yeah, and then so we'll have only 2 more lectures left today and Wednesday. Okay. Okay, great. So let's see what we're going to cover for today. Let's see what we covered in the last lecture. In the last lecture, we continue talking about quantization, and we formulate the rate distortion problem, and then we started giving examples of rate distortion, right? Like how to compute the rate distortion function RD, right? And this is the definition of the quantization in the scalar case. We covered that 2 lectures ago. And okay, and then we can use this Lloyd algorithm or k-means, if you like, to find the optimal, not optimal, to find a pretty good compression region and the quantization point, right? Quantization region and quantization point. Okay, and then we define a similar problem for vector quantization, right? Which can be more efficient to compress, right? Because we have the shaping gain, okay, for vector quantization. And this is the definition or the formulation of the rate distortion problems. So basically here, now you should be very familiar with the information theoretic language, right? It's all like that. Okay, consider what kind of sources, and then we define the decoding function, encoding function, decoding function, and define the error probability and define the rate, right? So here we need to define the distortion as well, right? Because distortion is something that we care about. Okay, here Fn is encoding function, Gn is a decoding function. Right here, one important thing we need to think about why we do this, right? Why we want to give any source information to some indices, right? Why only index? Why we don't go from here to here directly, right? The reason is that so we assume at both encoder and decoder they have the codebook, right? The codebook is known, then we don't need to transmit the codebook, right? We only need to transmit the index. Okay, this is the similar as all communication and compression system, right? We only need to transmit the index, right? Because both transmitter and receiver, or both encoder and decoder, know the codebook. Okay. All right, and for the distortion, we consider a very special form of distortion. So that's additive distortion. So it's given by this, right? So the total distortion equals to the summation of the distortion of each individual element. Okay, and then we say, okay, so this is the average distortion, right? So we do expectation of the, right? So the 2 most popular example of distortion we use is number 1, Hamming distortion, number 2, Gaussian distortion. Okay. So normally we do not use any other kind of distortion. The reason is that we cannot get the closed form of RD, of the rate distortion function, if we use some other form of distortion normally. Okay. All right. So let's see. Okay. So then we need to define the distortion problem. So basically we have upper bound for the distortion, and then we say RD is achievable if there's a source, and then we have a distortion measure D, and there is reconstruction of a bad X hat, and then this distortion is achievable, right? So the achievability, we didn't write here? Okay, we didn't write here. So you know what is achievable here? Oh, here. The achievability basically means that, so as long as n goes to infinity, so as n goes to infinity, and then the distortion constraint is satisfied, and then we're fine. Okay. Again, so we're in the long region long n region here. Okay, long block length, and the rate distortion function is defined by this, right? It's the infimum of R, and then for all the RD is achievable, right? For the distortion rate function is the reverse thing, right? It's infimum of D, and then RD is achievable, okay? So, and then, so we say, okay, so this is Shannon theorem. So the rate distortion function is nothing but the minimization over px hat given x, and under the distortion constraint, and then we minimize the mutual information based on that. Okay, and you may imagine that, so this is kind of similar to the capacity problem, right? The capacity is on the opposite, right? It's maximize the mutual information between x and y, where x is the transmitted signal and y is the received signal. And here, so we have this constraint as well, but it's a power constraint, right? But here it's different, right? So here, if we do the maximization, so here it's px, it's a distribution of x, right? And here, so with minimization, then we do minimize it over px hat given x, right? And we showed that before fixed px, so mutual information is a convex function of px hat given x. Therefore, this is eventually a convex optimization problem, right? We can use the KKT condition to solve it without any problem, right? So the idea exactly the same as before, okay? And so this looks like a channel, right? Px hat given x, right? X is input, x has output, right? So this is also a channel. We call that test channel, right? Because it's not a real channel, okay? All right, and then we just start giving a example on how to find the rate distortion function. So basically, we consider a Bernoulli source, right, with only 0 and 1. I think in your homework, you're gonna compute this with a uniform source with uniform distribution, okay? But the idea is exactly the same, okay? So we didn't finish computing that, so let's continue doing that now. Let's see. Okay, yeah. Okay. Today, so first we're going to see 2 examples. Okay, and then let's see, then what? Oh, yeah, and then we'll talk about the analytical method to characterize the rate distortion function, right? But here we do not do the detailed steps here. So yeah, because that will take maybe 2 lectures. So for rate distortion, the analytical approach is much more complex than that for the capacity maximization. The idea is the same, but it just formula is too complex. Okay, and if we do have time, then we're going to see the famous Arimoto-Blahu algorithm. Okay, to find the rate distortion function. Okay, so very good. Okay, first let's continue consider the Bernoulli source. Okay, binary source with Hamming distortion. Okay, so yeah, we give an introduction on that. So basically here we assume the input is x, and so the input is x, and then the output is x hat, right? So yeah, after some manipulation, we say that, okay, so equivalently, we can model that as a reverse channel. So which basically means that we have x here, and x hat here, and x here, right? And then we can build this channel. Okay, so because we have a Hamming distortion, right? So expectation of the Hamming distortion will just give you the probability that x and x hat are not equal, right? Therefore, so we can model this as follows. So from x hat to x, so this probability is 1 minus d, where d is a distortion. And this probability is d, and this probability is d, and this probability is 1 minus d. Therefore, in this case, we have a binary symmetric channel. Okay, so this is called backward channel. So kind of confusing here. So this is a backward channel, but before, so px hat given x, so that is a test channel. Okay, so this is a reverse. This is a px given x hat. Okay, so now we know the probability distribution of x is 1 minus p here. So here's 0, here's 1, right? And then, so here's 0, here's 1. So let's assume that the probability of x hat equals 0 equals to 1 minus q, and the probability that x hat equals 1 is q, right? Okay, given this, because of this channel, so we can basically compute the q analytically, right? How can we do that? We can just do this. So basically, it's 1 minus q times the transition matrix, which is 1 minus d, 1 minus d, d here. So that equals 1 minus p and p, right? So we can have this formula. And see, from here we can see, okay, we have two equations, only one variable, so we should be able to solve it, right? So let's see how we can solve it. So we can just compute it, right? So basically, 1 minus 1 minus q and q, so that equals to what? So 1 minus p times the inversion of this matrix, right? Okay, then we can see that so how can we compute the inversion of this matrix? Yeah, hopefully still remember it. So outside is 1 over the determinant, right? 1 minus d squared minus d squared, and whatever inside is these two. I think we need to exchange it, but here they're the same, right? Here we have minus d. Okay, so that's the inverse of this matrix, and then you can see that just do some computation. So we can compute that first. So that's given by 1 minus 2d. And whatever inside is basically this guy multiply this guy, and this guy multiply this guy, right? So that is 1 minus p times 1 minus d minus pd. And the second term is 1 minus p times d, or minus here, and plus 1 minus d times p. Okay, so that's basically it. And from here, you can get q equals to what? P minus d over 1 minus 2d. So you can, so basically, yeah, q equals to this guy, multiply this guy, and you can compute that, okay? And 1 minus q equals to 1 minus p minus d over this. Okay, very good. And now we need to make sure one thing, right? So this guy has to be less than 1, and this guy has to be less than or equal to 1, right? So therefore, on the top, it needs p minus d less than or equal to 1 minus 2d, right? It's a probability, okay? Therefore, we can get d is less than or equal to 1 minus p, right? Similarly, for the second equation, we still have the same thing. So this guy has to be less than 1 minus 2d. Therefore, can get d minus than or equal to p, okay? Therefore, we get d is less than or equal to the minimum of p and minus p. Okay, so yeah, before here, we can assume that, what we assume is the probability is p is less than or equal to half, right? Just for our convenience to characterize it, right? So it doesn't really matter. Okay, therefore, now we can compute the rate distortion function, right? Let's see when d is less than or equal to p. Okay, so because p is less than half, then we just need, so this guy will becomes p, right? Because we assume p is less than or equal to half. Okay, so yeah, if not, I mean we just do 1 minus p, which is almost the same. So okay, then let's compute the mutual information, right? We want to minimize the mutual information, right? So this equals to this guy, right? So why do we extend in this form? Because this is easy to compute, right? And because of that, we get the backward channel, right? Okay, and then in our last lecture, we derived that. So this equals to entropy of the error. Okay, because we can understand that as an additive channel, right? So we just add an error equals to x hat. Yes, and then so this equals to what? The first is the binary entropy function because we have a Bernoulli source, right? For the second one, we know this error would be distributed. It's a Bernoulli variable distributed according to d, right? Therefore, the second term is this guy. Right here, we have everything equal, right? Before we have we need the upper, we need a lower bound for this, right? But now everything will be equal, okay? So just think about why we can have an equal sign. So here we make sure that the error is independent of x hat, and here equal is that. So we make sure the error is exactly distributed according to d. Okay, so that's why we get equal sign. Okay, great. And this is when d is less than or equal to p. When d is bigger than p, and then what do we do? Right, so here, so basically if d has to be less than or equal to p in this case, right? If d is equal to p, is bigger than p, so that will be not a valid distribution, right? So basically in this case, we just let x hat equal to 0 with the probability 1. Okay, in this case, so basically what we got is that the mutual information of this is basically 0 because it's a deterministic variable, almost deterministic random variable. Therefore, the RD will basically equal to 0. Okay, so basically it means that we don't do anything, right? Therefore, so the RD is given by the following, right? It equals to this guy when d is less than this, right? And the 0 when d is bigger than the minimum of p and the 1 minus p. Okay, any questions? Okay, great. Yeah, I mean that's how we characterize the rate distortion function, right? If you like, so basically we can sketch it. So this is our d, and this is d, and normally it will be something like this, okay, and attach here. So here is basically the d max, right, such that the rate distortion is not 0, or let's say if p is equal to half, so this will be half, okay. All right, and if d equals to 0, right, basically means that we do not have any distortion. So if we do not have any distortion, then it's a lossless compression, right? Then the best we can do is what? Entropy, right? Therefore, so this point is give you 1. Okay, so that's a rate distortion function. Yeah, for rate distortion function, you always see this kind of shape. Okay, and you may imagine, okay, so we can show two things here, right? One is that rate distortion is a concave function, number 1. Number 2, rate distortion is always non-increasing, right? Okay, you can show that on your own, so we will not show that in class. But those are important property. Let's see, what do we use here? Okay, second. Yeah, let's see another very important case, which is the Gaussian sources with squared error distortion. squared error distortion. Okay. Okay, so far we assume the discrete memory source, okay? But we can show the same thing for the continuous source as well, okay? So these are just continuous, okay? So basically, we say the rate distortion theorem generalizes to well-behaved continuous value sources and unbounded distortion matters. Okay, so here we assume that x and x hat, they're all in the real domain. Okay, and here, the distortion can be unbounded. So here, let's introduce a theorem to describe the rate distortion function for these sources, for the Gaussian sources. So basically, the rate distortion function for an ID Gaussian source x distributed like this with quadratic distortion okay, dx x hat equals to this guy. Okay, and then the distortion function is given by the follows. Okay, let's see. This is given by RD or equals to, again, the piecewise function half log sigma square over d for 0 less than d less than sigma square, and 0 or d is bigger than or bigger than sigma square. Okay, so that's a rate distortion function. Okay, let's try to compute it. Okay, again, the rate distortion function looks like this, right? The minimum of mutual information. Right here, so we need to design the PDF instead of PMF, right? And then the distortion metric will be the same as before. Okay, and here is nothing but x minus x hat square. Okay. Okay, so now, let's try to characterize the lower bound here. Okay, so normally we need to compute the lower bound first and then see whether the lower bound is achievable or not. Okay, so the way to compute the lower bound is the same as before. So basically, we have differential entropy minus the conditional differential entropy. Okay, so the idea is the exact same as before, right? So here, we're still doing that in this way, and from here, we can get a backward channel. Okay. So here we can say use this, right? So basically what we do is that we can minus x hat given x. Okay. Yeah, before we use plus, right? Because that's binary. But then, so eventually what we want to do is that one x hat add an error equals to x, right? So this is basically the error. Okay, I want to add the error, then we need a minus sign here. But it doesn't matter too much. Okay. So next step is what? Do you remember? So basically what we do is that we have a lower bound in this step, right? Because we can drop the condition here, okay? Condition is always increase the entropy, doesn't matter the differential entropy or the entropy, right? Then we can do some computation here. So this guy is what? It's a Gaussian distribution, right? We know that. So the differential entropy is given by half log 2 pi e sigma square, right? So that's basically the differential entropy for a Gaussian random variable, right? And then how about this guy? Okay, so what can we do for this guy? So we may not know this, right? Because it's kind of up to design, but we know a lower bound of this means that we know upper bound of that, right? Let's say so this basically means that so if we fix the variance, right? Because that is basically the variance of this, right? Then what maximize the differential entropy? Right? Fix the variance, what distribution maximizes the differential entropy? Gaussian. Yeah, Gaussian, right? We just let this to be a Gaussian, and then we can have 2 pi e d, okay? And then that equals to basically sigma squared d squared, okay? And if we see this, so it's exactly the same, okay? So it basically means that this is achievable, right? So now we need to solve two things, right? So the first thing we need to solve is, okay, for this 2, would that be achievable, right? It has to be achievable, it has to be equal, right? We don't want the inequality here, okay? So when this can be achieved, I mean, when the equal sign can hold, as we said, right, the reason we have a larger than or equal to is because we dropped the condition here, right? If this and this are equal, it basically means that x hat and x minus x hat has to be independent, right? So if x minus x hat and x hat are independent. Okay, so that's condition number 1, right? Condition number 2, so when this will become equality, right? When this and that be equal, right? The reason we have an inequality here is that we use this, right? That's the upper bound, right? When they're equal, it basically means that if x minus x hat follow a Gaussian distribution, right? So if these two conditions satisfied, then that will become an equal, not inequality, right? That clear? So basically, based on this idea, so we can build, let's say this is the first step, okay? The second step is to make sure, this is indeed achievable, okay? So basically, what we can do here is that we can build this backward channel, satisfy the property we need, right? So basically, what we do is that we have x hat, right? And then we add a noise here, right? And then we have output, okay? And this noise is independent of x hat, okay? This noise is, right? We know that the next x minus x hat. Right, so make sure the distribution of this, so this guy and this guy are independent, okay? So, and then we need to make sure that, so first we need to make sure x and e independent, and secondly, we need to make sure e will follow a Gaussian distribution, okay? Does that make sense? So if E follow this kind of distribution, then x hat will follow a Gaussian distribution with sigma squared minus d, right? And then they're independent. Okay, so now it's very clear, right? So now we just let x hat follow a Gaussian distribution with this variance, and E follow a Gaussian distribution with this variance, right? And xe are independent. So we just construct this kind of variable, right? You can see that the summation of x hat and E will follow a distribution of x, right? Because Gaussian plus Gaussian is a Gaussian, and then we just need to add the variance here, right? Is that clear? Okay, then we can show that in this case, we can show the rate distortion function is as follows, right? So when d is bigger than or equal to sigma square, then Rd will be bigger than or be equal to half log sigma square over d, right? And if d is, d is bigger than, no, d is less, right? So not bigger. D is less than or equal to. When d is bigger than or equal to sigma, right? When d is bigger than that, so this does not make sense anymore, right? Because that will be less than 0. Okay, therefore, it means that, so this guy will be equal to 0. Okay, so how to make it equal to 0 is very easy. We just let x hat to be a constant. Then we're fine, right? So achieved by let x hat equal to 0 with probability 1. Okay, and then we're fine. Okay, that clear? So that will be the distortion function, and if you want to sketch it, it'll be very similar to before. So basically, it'll be like this, right? Let's do this for a simple distribution, right? Let's say x follows 0, 1, standard norm distribution. Okay, and this will be our Rd, right? And here d will be equals to 1, basically. Okay, is that clear? Okay, yeah, that's what our two examples here. Okay, so now,
One question.
yes.
Just can you go back one slide?
Mm-hmm.
Why was it that like the conditional entropy there is the same as the like x minus x hat entropy? Or
Yeah.
Not like the very first step.
Very first. From here to here?
Yeah, from there to there.
Oh, yeah, because yeah, this is a given, right? So this is a shift invariant property. Yeah. Yeah.
I think you have a typo in the last line.
Oh.
Where you said log of sigma squared over d squared.
Oh, yeah, d, not d squared. Yeah, so d is already squared. Okay, here's good. Okay, great. Okay, so now let's see how we can interpret this result. Okay, so yeah, now mathematically work out, right? So can we interpret it? Right? We kind of mentioned that twice before, but now let's make it a bit more specific. So now let's recall how can we interpret the channel capacity, right? So basically, if you remember, we say, okay, so this is the space, this sphere is the space that for all the received signal, right? For all the received signal, so the radius is nothing given by p plus the noise, right? And now we need to do sphere packing, right? So basically, for every transmit signal, we need to fit someone here. The variance of each one is what? Square root of np, right? And not np, n. Yeah, it should be square root of n times the noise, right? Because for every code word here, right, it can spread a little bit, right? And then we have a bunch of them everywhere. Okay, then what do we do with that? So the capacity is nothing but, so how many squares we can fit here? How many spheres we can fit here, right? That's the total number of distinct code word we can transmit, right? And the log of that would be the capacity, right? So the number of spheres equals to, let's see, Vn, so that's, a constant. Np plus n power n over, so that's the volume of a sphere, okay? And do another one, right? And then this will give you 1 plus p over n half, okay? And then r is nothing but take a log of this guy, right? And then it will give you yes, log 1 plus P over N. Okay, so that's the interpretation of channel capacity. Okay, so for here, we can do something very similar, right? So here, what we can do is that, so now we have a source. Okay, so this is all the values, all the possible values in the source. It's a Gaussian distribution, right? So basically, it's a Gaussian distribution, and what's the radius here? It's n square root of n times the variance, right? Variance is sigma square. Okay, so that's the radius here. All right. So now we want to. So this is all the possible source information. Okay. So now we want to quantize it, for example, into some code word. Okay. And for each code word, we allow a distortion of d, right? Which means that, okay, let's say here is a code word, right? And we allow maximum distortion of d here, right? So therefore, the radius here is square root of n times d, right? Because we allow this distortion, okay? So now what we do is that we need to do another one here, and possibly another one here. Okay, the goal is to cover this sphere, right? If we can cover all the possible code word, I mean all the possible messages in this sphere, and then we're done, right? So it could be a little bit bigger, right? Do this, and we're gonna see how many small spheres we need in order to cover the big sphere. Does that make sense? Okay, so basically what we do is that we need to count the number of spheres okay, in order to cover those, right? Then we just compute the total volume here is nothing but this guy, sigma square. Okay, and the volume of each small sphere is this one, right? And then clearly this is sigma square over d n half. Okay, and then if we take a log of it, so r will be nothing, 1 over log of this, right? And then it will give you, okay, so that's how we get this number. Okay, it's called sphere packing. Okay, so if you think these two steps, yeah, one is okay. So as long as, we need to, yeah, so not sphere packing is the other one, called sphere covering. Okay, yeah, this is sphere packing. Right here, it basically means that, so I have this volume, okay? Just pack as many as possible, as long as, the volume is not bigger than we're fine, okay? And for this guy, it's the opposite, right? Okay, we still have this volume, but we need to cover it. So here, if there's something left, it's okay, right? But here, we cannot let anything left. We need to cover the entire thing, okay? Therefore, here we have upper bound, and here we have a lower bound. Right, that makes sense, sort of. Okay, and for the discrete case, we can sort of, interpret in this way. Okay, so basically, we also did that for the capacity case, right? So here we can imagine, we have this two set here. Okay, so this is x hat, and this is x. Okay, yeah, for simplicity, let's just consider a discrete case, right? So the total size here would be what? Right, because most likely it will fall into the typical set. Okay, so now let's say for any point in the x hat, right? So correspondingly, it will correspond to a group of set here. And the size of it, that guy, is 2 NHX given X hat. Okay, so one guy will corresponding to a group here, right? Because all of this will be quantized here, right? Therefore, you can see in terms of the chipability, what we're going to do is what? Is a typicality coding as well. We just, for any X, we just find, X hat that's typical with that, and then we pick this X hat as a point we're going to do the quantization, okay? And, and for each point, we'll do this, and so on, right? And therefore, so basically, eventually what we want to see is that we want to see, okay, for this entire circle, how many small circles here we can pack, right? So basically, in total, we have this number, right? And then for each X hat, so it consumes this amount of elements, right? So that's n hx given x hat, right? That equals to 2 power of the mutual information. Okay, so that's why we have this mutual information here. Is that clear? Okay, yeah, that's intuition. I think that's good enough. Then we're now going to prove the theorem, so you can take a look at the book. The proof idea is exactly the same as before, okay, but there's some technical details that are different. Because we're operating on a different function, we need to use a different convexity and so on, okay? So now let's talk about a little bit on the analytical method. Okay, analytical method basically means that so everything we have seen so far is to use some special approach here, right? For example, let's say how we characterize the redistortion function here, right? We write down the lower bound and see, okay, so this step can be resolved, so the equality can be met, right? And okay, this step, the equality can be met, and then we have it, right? But that is not a universal approach, right? What if we cannot do that? Okay, so then we come back to this, the most rigorous but complicated approach, right? We solve the optimization problem, okay? So as we have seen before, so RD is nothing but I want to minimize. Here, because the minimization, we just write a Q here, represent that is a variable, okay? And then the distortion function, we need to write everything out to see the structure, right? The distortion is nothing but px times q x hat given x, and the dx x hat will be less than or equal to d, right? And what is here is the mutual information. Okay, but here, in order to compute it, let's write this mutual information out, right? So this mutual information equals to nothing but this guy, px and qx hat given x log qx hat given x over px, right? So this is the definition of the mutual information. Okay. Right now, let's rewrite this a little bit, and then basically we can get a optimization problem, right? So our goal is to minimize the mutual information, which is this guy. Okay, and the subject to, we have a few conditions here, constraint here. The first constraint is the distortion constraint. The second constraint is what? Is the constraint here, right? So if we do a summation of x hat here, it has to be equals to 1 for all x, right? We have one more constraint, which is for all x and x hat, q has to be, our variable has to be bigger than or equal to 0. Okay, so yeah, this is a standard form of a convex optimization problem, and then we just solve it using KKT condition. Okay, so the idea is exactly the same as before, but because the format of this is very different. Before, our px is a variable, right? But now q x hat given x is a variable, so it becomes much more complex, right? So yeah, I will probably upload a video. Yeah, I did that before, but we don't have time to do that now. Okay, it's a very lengthy derivation. Okay, and I removed homework using this. Okay, but if you like, in my video, I cover more problems than our homework 5. So you can take a look how to solve those kind of problems. It's very, very complicated. Okay, in the book, so it lacks of detail. So, but I have a video including all the details. All right. Okay, so next, yeah, we'll have maybe 1 or 2 more minutes. So I'll start talking about one very important algorithm. It's called Arimoto-Blackwood algorithm. Okay, so as we said before, even for this analytical approach, it's very complicated, right? Normally, when you solve a convex optimization problem, it may not give you an analytical approach. Okay, it may not tell you RD equal to a nice formula exactly. Okay, yeah, do you remember? So for the channel coding problem, for the channel capacity problem, from the KKT condition, so what I get is okay. So we know there are some good letters, there's some bad letters, and we should now use the bad letters. And for all the good letters, right, the capacity should be the same. Okay, yeah, we can get similar things here. Okay, but in order to characterize RD, in practice, computing RD is more challenging. Normally, it's more challenging than computing the capacity. Okay, therefore, even if we cannot characterize it analytically, and also, the analytical expression may only work for the Hamming distortion and the Gaussian the square error distortion. So what do we want something else, right? So then we develop an algorithm to characterize it numerically. Okay, so this is the Arimoto-Blackwood algorithm. Okay, let me give you the idea of it, right? So in practice, let's say, okay, so we have 2 sets, A and B. Okay, so let's say, how can we find the 2 points on these 2 sets that are the closest? How can we do that? Right, if we want to find, let's say, the distance here is a Euclidean distance, right? How can we find, 2 points, one belong each side, that their distance are the smallest? How can we do that numerically?
Compute all of them and then find the smallest?
Yeah, of course, you can. But what if they are continuous? Yeah, one way, don't think, we can think in this way, right? Let's randomly pick a point here, okay? And then how about we find the point that is closest to this guy, which is probably here, okay? So now we find a point, and then how about we pick this point and find the point that's closest to this guy from here, right? Then we may find, okay, so this guy may be the best. Right, and then we will repeat, okay, probably, okay, find it here, and so on, and then do this repetition, okay, and then, until it converge, they do not move anymore, then probably that's the closest, okay, and so for this kind of thing, normally we cannot guarantee the optimality, right? But if these 2 sets are convex, we can guarantee that the optimality of this algorithm. Okay, so here to compute RD, we're using the same idea, similar idea, but now we're now work in some convex set. Okay, so let's say we work. So here represents some probability distribution, and here represents some probability distribution. Okay, and how about that? The distance here. So what is the distance? Right, before we can use Euclidean distance, but here is probability. So how can we say these 2 distributions are kind of close to each other? KL divergence, although it's not a distance, right? But yeah, we can use KL divergence or relative entropy. Okay, so far so good. However, we have one problem. When we want to do this minimization problem, only this guy is a variable, right? But here, we need two variables, right? So here and here, so both of them can be changed, right? So RD is only has one variable, px hat given x, right? But now we need two variables. Okay, so this can sit in here, okay, no problem. But we need some probability distribution here. What should we do if we want to use this idea?
Could we just make one up?
Yeah, that's right. But how? You were gonna make something up. Yeah, the idea is totally correct. Right. So yeah, in the next lecture, we're going to tell you what are we going to make things up, right? And from here, you may guess. You may guess already, right? So for mutual information, either we maximize it, optimize it over this guy, or we optimize it over this guy, or over this guy. Okay. So we're going to, pick some of these guys that make sense. Okay. In the next lecture. Okay. So great.